Okay, this is the first time I'm trying to do this, so we're gonna try and keep some notes down to about 5 minutes and take this at a little chunk at a time. And our goal for today is to develop the idea of moment of inertia of a single object moving in a circle. Okay, a single object of mass m. All right. Now, if you remember from last time when we were talking, the idea of moment of inertia is we are trying to find the rotational equivalent to F equals ma, right? And we said that torque is our rotational equivalent to force, angular acceleration alpha is our rotational equivalent to linear acceleration, and so we called the moment of inertia I this rotational analog to mass. So it's important to remember the moment of inertia represents how hard it is to turn something, right? The bigger the moment of inertia is, the greater the torque you're going to need to turn it. Okay. So now, oddly enough, though, to work out what our equivalent is for mass here, okay, we are going to use the concept of kinetic energy, because we can describe the kinetic energy of this particle moving in a circle, okay, of radius r by its linear velocity, 1/2 mv squared. And the goal is to get something that looks like here, as well described rotationally, since it's also going around in a circle, okay, to look something like 1/2 something times omega squared. And that something, whatever it is going to be our moment of inertia. Okay. But here's where we're going to use our connecting equation. Okay, since if this thing's going around the circle with speed v and radius r, then it's also going to have a constant angular velocity of omega, and v is going to have to equal r omega. So we're just going to replace v with r omega for our kinetic energy. So v equals 1/2 m, and then r omega squared. So that means we'll be able to rewrite this as 1/2 m r squared omega squared. But that's exactly what we want. We wanted something that looks like here, 1/2 something times omega squared. And if we compare that with I, there's our moment of inertia. So I is going to equal 1/2, or oops, not 1/2. It's going to equal mr squared. Okay, so that's for a single point mass at a distance r r from the axis of rotation. Now the good news is that if we have several objects turning all together, we could go through the same process, but it turns out that to find the moment of inertia of those objects going together, but the total moment of inertia is going to separate out, since each one is going to have its own kinetic energy, and each one is going to have something that looks like replacing their particular velocity with r omega squared, and the omegas will be the same for all of them. We'll have that the total moment of inertia is just the sum of each individual moment of inertia, and so on and so forth. So that means here that we can also express for multiple bodies moving together that the total moment inertia is going to be the sum of mi ri squared, I equals 1 to n. Okay, so that means that we can always put together objects and just add up their moments of inertia. And this is going to be true for solid bodies as well. All right, that's all for now. Next time, we're going to work on how to compute the moment of inertia for solid bodies. And we'll start with some simple objects and build from there.